Hey there, Hampshire chemistry students. Glad to have you here today. In this video, we're going to be taking a look at how to understand how we balance chemical equations together. So, to understand what we mean by balancing chemical equations, we need to understand what the law of conservation of mass means. Very simply, it's this idea that mass can never be created or destroyed in a chemical reaction. So, this is something that the universe cannot break. It is a 100% rule. So, how do we apply this to chemical equations? Well, we need to make sure every equation we write in chemistry is a balanced equation. Now, when we understand what a balanced equation means, simply it is when we have the same number of elements on both sides of a chemical reaction. So the products and the reactants have the same thing. So let's see what that looks like here first by looking at an unbalanced equation. So here I have an equation for the synthesis of ammonia. I have nitrogen plus hydrogen as my reactants, creating NH3 on the other side, ammonia. Now, first off, you might notice that there's some weirdness here. And that is if you've been paying attention to your vocab, because nitrogen and hydrogen are special types of elements called diatomic elements. Okay, these elements always exist as two atoms. Why two? Well, they are diatomic. This is the most stable form they'll ever have. So I want to make sure that whenever I write elemental nitrogen, that's like nitrogen by itself, it gets a 2. And same thing with the hydrogen. It also should get a 2. Same with any of these other elements when they're not paired with someone else. Notice how this nitrogen doesn't need a 2? That's because it's got the hydrogen hanging out with it. So, also we want to make sure we're starting to understand when we write chemical equations is to write the states of matter that are present. The states of matter are very simple. There are 4 kind of possibilities. 3 of them you already know. Solids are represented with an S, liquids with an L, gases with a G, and one we're going to take a look at in a second is the idea of aqueous. Aqueous simply means being dissolved in water. In this case, I know that nitrogen exists as a gas, hydrogen exists as a gas, and so is ammonia most of the time. Now, you might not know that off the top of your head right now, but that's okay. We're just making sure we're getting used to writing our reactions. So, this is still unbalanced. How do I know? Well, I can start to count up my elements. The easiest way I tend to write this is I start here in the center and I write what elements I have. I have nitrogens and hydrogens. This is what's on both sides of my chemical equation. So right now on the left side I have 2 nitrogens because I have N2. And over here I only have 1 nitrogen because there is no subscript there. Whereas over here with the H2s, we have 2 hydrogens on the left and we have 3 on the right. So we are currently not obeying the law of conservation of mass because we have different amounts of nitrogen and hydrogen. So what I'm going to need to do is I'm going to need to fix that. So very simply what you're going to use is not little numbers. We can't change these formulas. Right? Hydrogen always has to be H2. Ammonia has to be NH3. So I'm just going to increase the amount of these that I have. So I need 2 nitrogens over here on the right. So I'm going to place what's called a coefficient, a big number out in front of NH3. What this does is it means that I have 2 of these NH3s. So 2 NH3s would have a total of 2 times 1, 2 nitrogens. And that makes our nitrogens balanced. That's nice and easy. Now, because this also affects the hydrogen, though, I have 2 times 3, 6 hydrogens now on the right-hand side. You always want to make sure if you're affecting more than one element to keep track of those. So over here, then, our nitrogens are happy, but I need to make my hydrogens equal. So I'm going to place a big capital 3 in front of the H2, so that way I have 3 times 2, 6 hydrogens. 2 and 2, 6 and 6. This is now a balanced chemical equation. Let's take a look at a quick, trickier one maybe. Here's an example of a combustion reaction where I've got some solid fuel reacting with oxygen gas to make liquid water vapor, or excuse me, water vapor as a gas and CO2 as a gas. So here I've got carbons, hydrogens, and oxygens. I'm going to go a little quicker here. 10 carbons, 8 hydrogens to start, and 2 hydrogens. Here I have 2 hydrogens. I have 1 carbon. Now you got to be careful because here's a tricky one where we have an oxygen here and 2 oxygens here. And since these are added together, I have 1 plus 2, 3 oxygens total on the right-hand side. So let's fix everybody in here. I like to always start with my carbons and my hydrogens for these combustion reactions because wherever there's more than one, you end up having a lot of trouble. So I'll save those oxygens for last. So I need 10 carbons. So why don't I just go ahead and put 10 in front of the CO2 because 10 times 1 gives me 10 carbons. Hydrogens, I need 8. So I would need to put a 4 in front because 4 times 2 equals 8. Now I have to count on my oxygens on this side. So I have to do both of these at the same time. 4 times 1 gives me 4 oxygens. 10 times 2 gives me 20 oxygens from those carbon dioxides. So my total number of oxygens on the right is 24. So my carbons are balanced, my hydrogens are balanced. Now I want to fix my oxygens. So I only have 2 on this side. Since they come in packets of 2, I'm going to make sure that I'm going to put 12 because 12 times 2 gives me the 24 oxygens I need. And really that's as hard as it gets with balancing problems. You need to just count on both sides and make sure they work. Where things get more interesting is where we look at examples like from our lab yesterday, where we have to use our understanding of balancing and chemical equations to do things like this. In station number 1, it asks you to write the balanced equation and include the states of matter for a reaction. In yesterday's lab, you mixed sodium carbonate and calcium chloride to create aqueous sodium chloride and a solid. So how the heck can we write this out? Now you're going to need to take the names of these and continue to make sure we write our formulas correctly. Those ionic compounds aren't going away. So sodium chloride, calcium chloride are going to need to be written down. And notice here in the middle it says to create something new, the sodium chloride and a solid that we need to predict. Now this to create is the sign that I'm going to be drawing my arrow in between. So I've already gone ahead and written my chemical formula as I've been told. I have sodium carbonate, correctly written with the 2 sodiums, calcium chloride with 2 chlorines, and then the NaCl. If you do not write correct compounds, your chemical equations will never be correct. Now, we already were told these guys were aqueous. Remember, that means that they were dissolved in water. So I'm going to make sure that I add aqueous to each of these as their state of matter. We were told that this last one was a solid in our lab, so I'm going to put an S for that guy. So we need to figure out what is this final atom? What is this final compound? And to do this, we need to think back to our types of chemical reactions. I need to predict what my last product is going to be. So we have to look back at some of our patterns. Okay? I know that this is not a synthesis reaction because these two will create, that would have 2 single elements. These are not single elements. Similar with decomp, this would not be decomposition because we have more than one reactant. Oh, single reactant, single replacement, we're getting close. We have a compound, but we don't have a single element it's reacting with, which tells me, since we don't have any of our combustion reaction components, we are dealing with a double replacement reaction. So to help me predict this reaction, I'm going to write out my double replacement setup here. So my A, my generic A is representing the sodium, and the B is going to represent our carbonate here. Remember, that is a polyatomic, so it sticks together. So my C is going to be calcium, and the D is going to be chlorine. According to our patterns here, we're going to see some swapping. Our first one said AD, right? That is the first pairing in a double replacement. And hey, look, that makes sense. Sodium was A, chlorine was D. Notice just because this chlorine had a 2, this chlorine doesn't have a 2 because it is being balanced by only one sodium. So what's left then is to make sure that we are reacting and creating CB. So let's look at what our pieces were here. C was our calcium, so I'm going to put Ca, and B was our carbonate, CO3. And I can think really quickly here, make sure that my calcium is a positive 2, carbonate is all minus 2. So I don't need to add any subscripts or parentheses here, so we're good. Now what's not good though is the balancing. The last step we need to take here, once we've identified our type of reaction and predicted our product based on our pattern, is to balance. We've already seen 2 balancing examples in this video. I'm going to leave this one for you guys to try on your own. You're going to need to put the coefficients to make sure things are balanced. I noticed right away, like sodiums, there are too many sodiums and too many chlorines over here, so we might need to fix that. Okay? The rest of this is up to you guys. Take some time, ask questions, and you're going to do awesome. Thanks so much for watching. Bye-bye.